Good morning. This is Lab 5. We're going to demonstrate momentum. And momentum is conserved. That's what we'll do. You'll see this. So this is a fun experiment. It works very well. It clearly explains that momentum is conserved. So if you recall, momentum, P equals mv. Now, momentum is a vector, the P. The V is a vector. We're going to do this in one dimension. So if you recall way back when, in chapter 2, we said if we're dealing with vectors and they're in one dimension, we can drop the vector notation. So we're going to drop the vector notation. We're just going to say P equals mv. Now, here's what you have to look at. We've got a system here. You got to define the system, okay? The system consists of a ball rolling down the hill, right there, okay? We'll call that M of the projectile, okay, MP, all right? Then we got a ball sitting right here. Now, it could be larger, smaller. We're going to do two. One will be a less dense and one will be a dense. But that's momentum of the target, MT, or mass of the target, rather. So the momentum of the projectile is MP V. Now this is the initial velocity, V0P. And the momentum of the target is MT V0 target. Which, if this thing is sitting stationary, V0 target equals 0. Wow. So that term is 0. So if my system is defined, let me do this in a different color here. If my system is defined as those two spheres colliding, then the sum total of the momentum of the system is that. Notice I have a 0 because that's the initial momentum. So that's P0 of the system. Now, when we did the lecture, you may recall, we said the way you do a momentum problem is you draw the pre-collision picture and the post-collision picture. Well, I submit to you that this is pre-collision. Post-collision is going to look something like this. The M1 is going to have some M projectile. It's going to have some V final projectile, and M target, which has now been struck, is going to have some M target. Those didn't change. V final target. So we're going to have a P final for the projectile, and we're going to have a P final for the target. And if you do this right, the sum of these should equal that. And that's all I'm going to say about the math setup. We'll talk a little bit later about the kinetic energy, but the concept is V0P, V final P, V final T. You need to go to ascertain what those are. And that's all I have. By now, you've determined, or you've been thinking about this, we need to know what some of these velocities are and how we calculate them. Just like every experiment we've done so far in this course, you've had to ascertain what the control variable is. Now, just think for a second. What do you think the control variable is in this experiment? if I take a ramp and I roll a ball, mass of the projectile, okay, it's got a velocity initial of the projectile. Now I can change the mass of this target, anything I want, okay? So that's an independent variable, this mass of the target. This never changes. This is a control variable. We have to determine the control variable. Now, how are we going to determine the control variable? That's the next step here. And with that, we'll... To determine this control variable, we're going to use the same exact, let me say that again, the same exact methodology that we used with the projectile that we launched in the second experiment. Remember, we launched a projectile horizontally and we tracked how far it landed. We called that the range, and we measured the height, which I believe we called Y0. And we watched how far this went. Then we had a range equation. I'll let you go back and look up what the range equation was. But we also had a way of calculating this by timing it. We knew what the height was, which is 1/2 g t squared. So I can calculate from the height of the bottom of the ramp, the launch ramp, to the floor. I know what that Y0 is. Gravity, by now, you know what that is. You can calculate time of flight, TOF, time of flight. Starting to look exactly like what we did in experiment 2. So we're going to measure this range, and we're going to say that the velocity initial in the x direction is right here. There's no acceleration or deceleration in the x direction. So we can say that the range equals v0x time of flight. You can calculate v0x. You need to get this one right, just like when we did that projectile, because all of our subsequent calculations depend upon that control variable. Okay, now I'm going to demonstrate this. I'm going to use a small ball. You can see that a little bit right there. That one has less mass than the steel ball. I'm just going to demonstrate it. So before I even demonstrate the collision, I just want to demonstrate the technique. This is going to be the same every time. It's a control. Now, you ask yourself, why can't I measure this height, mgh, and turn that into kinetic energy right here? And the answer is you could, except for one thing. We may have covered this already. I'm not looking at the syllabus yet. But this ball doesn't just slide, it also rolls. So some of the kinetic energy is in rotational kinetic energy. Some of it's in translational. So you wouldn't want to do that necessarily. But we do know that gravity is one-dimensional, so this works all the time. So all we have to do, if I can catch this, is if you have someone that's got good release, just hold this up against the same point, the post, and you let go of it. And you can calculate this velocity based upon the height. Okay, so I'm going to stop here. We're going to take a couple measurements. I'm going to set this up so that you can see how we impact this with on a piece of carbon paper on the floor. And that's it. Okay, I'm going to demonstrate the technique for how we get the first velocity, the initial velocity, V0 projectile, and that's our control variable. Very simple. I've already pre-measured where this is going to hit, and I've got a mark on the floor. I've marked the paper, so it's real simple. I can just drop straight down from where it's launched, and it's right up against the edge of this desk. And I go out here, and I mark this as some number. Okay, so I've got a 40 centimeter mark on the paper already. I'll mark it again just to demonstrate to you. There's my 40 centimeters. Okay, now, so I'm going to fire this thing. And again, just like the passcode launcher, this is highly reproducible. So all we're going to do is drop the ball, stand by, release, boom. Okay, and I'm done. Now I can do this 5 or 6 times, and I can ascertain what the distance is. So you can see very clearly, there's my 40 centimeter mark. I just have to add up there. And I've got the initial velocity calculated. And that's it. Now you've got the control variable established. You know what V0 of X is. So I'm going to draw this picture again. By now, if you haven't gotten the idea that you probably need to put a picture like this in your lab report, then I'm going to tell you, you need to put a picture like this in your lab report. Okay, hint, hint, wink, wink, nudge, nudge. You got to do it. Okay, and once you understand this, then it becomes easy. So now I'm going to put the target ball up here. Okay, so here's the target. So we've got mass of the target. We've got mass of the projectile. This is pre-collision. Pre-collision. Let's call the collision something like X. There's a collision. Pre-collision. Okay, now, what happens post-collision? Oh. So let's draw a dashed line down here that separates the two pictures. Okay, so now we got this separation. Post-collision, the projectile, and I'm going to color that in blue just to give a little change. So we've got mass of the projectile. That's never changed. We got V final of the projectile. Now, how do we determine that? Well, we're going to allow that ball to land at range of the projectile. Wow. Okay. And then what happens to the target ball? Well, it's collided and it's followed some trajectory. Just for the sake of argument, I'll put it out here. And we've got range of the target. So range of the target goes back to here, and range of the projectile goes back to here. And just like we did with the control variable, we say V of the projectile final equals range of the projectile divided by time of flight. Now, where'd I get time of flight? It's the same exact height from here to there as it was when we did the control variable. So if you were smart enough to remember to write down the time of flight, you've got it right there. And then we know this is the same height. So clearly that time of flight is the same, and we can say V final of the target equals range of the target divided by time. Now you've got two final velocities, mass times the velocity, mass times the velocity gives you the final momentum. Add those up, compare them with the initial momentum, you should have this experiment in the bag. That's all I want to say now. Now I've got two spheres. I've got target sphere set up, and I've got the projectile. I'm going to do one test. Now, if you look, it's a little difficult to see, but I tested these before we started the experiment. So I've got one piece of carbon paper way out here and one here. It turns out that the light bulb, the target, is going to land way out here, and the projectile is going to land somewhere here. Now, you may not be able to see this, but when we did the projectile by itself, it landed in this region. So that says the projectile is going to lose some velocity. Its momentum will be less. The target, which didn't have any velocity at all, is now going to land out here. So it's going to gain some momentum. So let's try this. And here we go. Perfect. We got them both exactly where we wanted them. And that's all I wanted to do.